Hi there. Welcome back to Core C++ Part 6. I'm Stephan Lavavej, Visual C++ Libraries developer, and today I'll be walking you through a new release of our compiler, which is codenamed Milan. It'll be officially available. There will be a link next to the page when this video goes up. Formerly, it's called the Microsoft Visual C++ Compiler November 2012 CTP, where CTP stands for Community Technology Preview or something. But internally, we just call it Milan. It's code name. And this is an early alpha release of some of the new C++ 11 features that we'll be bringing to you. And I've listed the features that have been implemented here. We've got Variadic templates, which we've been waiting for a while, raw string literals, explicit version operators, default template arguments for function templates, and then finally delegating constructors and uniform initialization. So I'll be showing you some examples of all of these cool things. But first, a few caveats. What I'm going to be showing today is a build for my dev machine that I finished just a couple hours ago. It's extremely similar to what we're going to be shipping in the CTP. When the CTP is shipped, it will be available as essentially as an add-on for your IDE. As it's been explained to me, you'll just need to set your platform toolset to something like v120_CTP, and you'll magically be able to use that instead of Visual Studio 2012 RTM. They asked if I could demo that, and I was like, I barely know how to use the IDE. Please don't make me do that. So what I'm going to be showing you is just running the compiler from the command line. It's the same compiler either way. The other caveats are that because this is a very early build, IntelliSense, which is powered by a completely separate front end, the EDG front end, has not yet been updated to take advantage of these new features. So if you write things like Variadic templates or explicit version operators, you may see red squiggles. Just power on ahead because the real compiler, which we call the front end C1XX, that one will accept your code even if IntelliSense doesn't yet recognize the stuff. We had previously seen something like this when we had shipped the range-based for loop in VS 2012 beta before IntelliSense support for it was released later in RTM. The other things are that /analyze for static code analysis, that's powered by a slightly different version of our front end. That also will not be supported in the CDP. It eventually will be by the time this ships in a production-ready form. And finally, and unusually, this does not contain any library updates for once the compiler is racing ahead of the standard library here. For arcane reasons, we basically need to wait for the CDP to be released before we can start taking advantage of it in the standard library. So in particular, we have not yet updated the standard library to take advantage of Variadic templates. We've still got our faux Variadic macros in there. And we have not yet updated various standard library containers to take advantage of explicit version operators or initializer lists. Although we have uniform initialization, which is the core language part with the curly braces, you will not yet in the CDP be able to initialize a vector by saying vector int v equals brace 1, 2, 3, close brace, semicolon. We've got to hack the standard library to add all those constructors. I'm looking forward to that, but we haven't done that work yet. So why don't I start showing you some examples. Some people had asked me earlier in the comments to show my working environment. And this is very similar to what I use in my dev box. I spend most of my day working just on a command prompt here, and then working in my favorite plain text editor, a slight clone of Notepad. So I'm just going to be driving the compiler like this. Remember, it's the same compiler as in the IDE. It's just that I'm driving it by hand. So if you've never seen this before, don't freak out. It's just the Visual Studio you've always used. So here I've got a command prompt with all of my various paths set. If I run the compiler, the driver is called CL. Nobody at Microsoft that I can find actually knows what CL stands for. I believe it stands for something like compile and link. This is the name of the compiler driver. And here you can see it's reporting its version number as October 26, which is today as I'm filming this. The version number of the CDP will be slightly different. And it shows usage. So if I take some source file here, here I've got kitty CPP, I can compile it. And here my usual command line is CL EHSC for exception handling, no logo to silence this banner, warning 4, because I always compile at warning level 4. When I build test programs, I always link them statically and in debug mode, unless I need to enable optimizations or something. the name of my source file, and then if that compilation is successful, then I just want to run kitty.exe. So I can slam this in, it'll compile very quickly, and it'll print hello world. So this is what I'm going to be doing over and over as I put in new examples. Okay, so let's do something a little more interesting than hello world. Let's look at raw string literals first. So imagine that I'm doing something like writing a regular expression in source code. I'm not even going to bother to include the regex header here. Imagine if I said something like, const regex r, and then I want to do something like match a source file or just a file name on my file system. If it's Windows, then paths are separated by backslashes. So if I just try to type something like, c:\temp \whatever.text, this is not valid because this string literal will be parsed by C++ first. And it's going to see, oh, \t, \w, what are you talking about? Because if I said, \n, we all know that's a literal new line. So I would need to escape these backslashes once for C++. And then because this is a regex, I would need to escape them again because the regex parses backslashes. So that's kind of obnoxious. The fact that I need to escape it for regex is unavoidable because sometimes I do want to write, oh, I want a regex, and I would just like to match against a word character one or more. If I'm writing this in a string literal, I need to double escape this for C++. That part is obnoxious. Here my editor thinks this is actually a file path. Other problems could be, what if I'm trying to write like HTML in a string literal in C++, or XML, one of those modern web formats. And if I say something like span class, here I'm just writing some stuff, equals, and then I put like a name, blah. And if this is a string literal, well, hey, I can't do this because these quotes will end the string literal. So I can't just write this directly. I need to escape those double quotes. So I would need to put backslashes in here, and this is ugly. Or imagine that I'm writing something like OpenGL shader, where I would like to just put the GLSL source code directly in my C++ program as a string literal. Well, there I'm going to have like new lines. So if I was writing, whatever code here, I would have to say \n if I actually want a new line. Putting all of those in there is obnoxious. Similarly, if I'm trying to write, multi-line HTML or XML, I'd have to put \n in addition to escaping all of the double quotes. This is basically terrible. C++11's feature raw string literals allows us to avoid all of this. So imagine if I say, instead of double quotes here, the simplest syntax for this is r double paren, and then I can put whatever I like here. So I could put meow, and then paren double. This is the new syntax. And then I'm just going to print it to cout. I could also print it to puts or printf, but I'll just use cout here. So if I save this, and then compile and run, I get meow printed. So that's great. I was able to print what I've always been able to print with a little extra syntax, but I can put cool stuff in here. So I could say like c:\temp \whatever.text. Here I'm writing single backslashes. I'm making no attempt to escape them for C++, but if I compile and run, now I get ctemp whatever text printed out. This is essentially a way to tell the compiler, okay, I'm just going to dump some text at you. I would like you not to specially interpret anything in there. Backslashes, double quote characters, new lines, backslashes at end of lines. I don't want you to interpret any of that until you see the special closing sequence, which is close paren double quote. So in here, in addition to these backslashes, I can put actual new lines in my source file. I could put double quotes, so something like hello world stuff. I could also have backslashes at the end of a line, which would, in normal C++, cause the line to be unwrapped. But here, the raw string literal just says, OK, I'm going to keep parsing that. Let's see, I've got double quotes. That's basically all the special stuff. I could say, \n, foo, \n, bar. None of this will be interpreted specially. And then I close it off. So something like this, save, compile. And here we go. I've got my backslashes, my double quotes, my backslash at the end of line, \n. All of these things are being preserved as they were in the original source code, and I just had to mark it as raw. So this is actually really awesome. It's useful with regexes, XML, all the things that I mentioned. But you might say, okay, well, what if my string actually contains the sequence parenthesis double quote? Then how would I tell C++, hey, you know, I don't want you to interpret this one as the end of the raw string literal? Well, the designers of this feature had great foresight, and they said, okay, you can put in arbitrary sequences between this double quote and this paren, and then you just need to repeat it at the end, and I'll match that. So if I say something like zizzy here, and I put it at the end here too, then inside here, I can put a plain, something like a paren double, which ordinarily would have terminated the raw string literal, and then I can say meow, and then actually close it with parenthesis zizzy double quote. So I can save this, compile and run, and it works just fine. I've got that parenthesis double quote here. It was not interpreted as the end of the raw string literal because I put in a special matching sequence here. You can put within some limitations, you can read the standard for exactly what's prohibited. I think it's like up to 16 characters of anything in the basic source character set. I actually like, instead of something like zizzy, I like just 2 twiddles because A, the sequence does not appear in anything resembling normal C++ or other syntaxes, and it's short and it's easy to search for. But you can put anything you like here. But by default, you don't need to put anything there if you're certain that the sequence, parenthesis double quote, does not appear in your string. So that's raw string literals. Nice and simple. Note that the companion feature Unicode string literals, where you can write U or U8 or capital U, which is very similar syntactically to raw string literals, that one has not yet been implemented. So all we've got here is raw. I believe that they also work with wide strings, although I would have to go look up exactly where the L goes there, and I'm certain that they've tested that. So it works with both narrow and wide. So that's raw string literals. Let's look at explicit conversion operators. So let me clear this out. Okay, so the motivating example here actually occurs in libraries like shared putter and unique putter that want to provide classes that are Boolean testable. So imagine that I've got some class, and here I can actually just call it a struct. I'm going to call it like smart putter. Okay. And imagine I've got constructors that store a pointer and do all sorts of cool things. I don't even really care about any of that. But eventually I would like, in my program here, to have a smart putter p constructed with stuff. And then later on, I would like to test it, because one of the things about raw pointers is that they're Boolean testable. So I'm used with raw pointers to being able to say things like if p, then go do something like, you know, dereference p, or I can also do it in a single line, if p and dereference p, relying on short-circuiting of logical and. I could also say or and things like that. I could say if not p and whatever. So if I want this thing to be Boolean testable, let me just complete the syntax here. True. Else. Still getting used to typing on this laptop keyboard. It's a new laptop. False. There we go. So if I've got this, I would just like to be able to make this work. So if you're looking through your C++ textbook, you can see, oh, I can write these things called conversion operators, or conversion functions, if you read the standard for a living. And the syntax for that looks like operator bool. And this is actually const. It's not going to modify the smart putter. In this case, I don't even have any data members. And here, because I haven't actually put any data members, I'm just going to say this returns true all the time. Here I would really be testing some internal pointer or whatever. So now I can convert a smart pointer to bool. This seems cool, right? And actually it will allow this to compile and work, but then it will do horrible things, and I will show you those right after I prove that this basic thing compiles and works. Let me slam this over to the side here. So compile my program. Okay, so at least if I say operator bool, I can convert the smart pointer to p. Now, notice how bool is a built-in type. That means I can't do anything like give bool a constructor from smart putter, because I don't control that type, and it's in the core language anyways. I need this conversion function that says, okay, I go from this class type that I do control to this built-in type operator bool. You can also write conversion operators that convert to things like std strings and other class types, where the source type is the one saying I'm convertible. But in this case, with operator bool, you have no choice. You must make a conversion operator here. So this seems reasonable, and many people actually stop here. But if they are battle-scarred library developers, they know that this is actually dangerous, because not only does this compile, but things like this compile. Suppose that what I was trying to do was say, I was trying to like dereference p, and then because that gives me some integer or something, I would like to multiply that by some number. And then I would like to print that out. Okay, imagine this is what I intended to write. And if this were a real smart pointer, this would compile and do the right thing. But imagine I make a typo. My finger slips on the laptop keyboard, and instead of writing deref p, I just wrote p times 1729. This is bogus. This is totally bogus and should not compile, because it doesn't mean anything to multiply either a raw pointer or smart pointer by some integer. That's just like bogus. However, as written here, because I've got operator bool, this will compile. This is exceedingly bad. I'm just going to show you that it compiles, and then it prints out something completely ridiculous. Wow, it compiled and it printed 1729. I can totally multiply pointers by integers. You know, WTF. And the reason why this is happening is because C++, it's sort of a deep thing. C++ really trusts you, the programmer. And it assumes you know what you're doing all the time, even when you might not. And because you wrote some code and you gave it to the compiler, C++ would really like to compile that for you. It will go to relatively great lengths in order to do so. There are limits. It won't do completely ridiculous things. But in this case, it does something that's kind of unintentional. What happens is that if you write a smart putter and then you provide an operator bool, and then you write something like p times 1729, the compiler says, OK, programmer's writing something. I need to make this compile. Can I? Well, I can't directly multiply smart putter by 1729 because it didn't overload operator star, binary operator star, either as a member function or a free function. It does name lookup, as we've seen, and overload resolution to figure out whether any of those are in scope. OK, so I can't directly multiply the thing. Can I make this compile any other way? Now it's getting increasingly desperate. It says, oh, cool, smart putter has a conversion operator to bool. That's a user-defined conversion. I can invoke one of those. It won't do two, but it will do one. And then it's got a bool. And it says, OK, I've got this bool, and they're still trying to multiply it by 1729. Oh, I know how to make this work. I can then do a standard conversion from bool to integer. That's not a user-defined conversion. That's between two core language types. So it's totally willing to do a UDC, user-defined conversion, from smart putter to bool, and then a standard conversion from bool to integer, and then it can multiply two integers, and it's happy. This is totally legitimate according to C++, and that's why this compiles. And yet we don't want it to compile. So in C++ 03, this was a problem for anybody writing smart pointers, anything that wants to be Boolean testable. There are hideous hacks to actually make this kind of work without allowing bogus code like this to compile. You can look at your standard library headers to see what we've done in Visual Studio 2012 and previous versions. If you provide a conversion function to pointer to member, either pointer to member function or pointer to member data, then you can get something that's still Boolean testable, but not really useful for anything else like multiplying, except that it looks hideous in the source code. It can actually be less efficient depending on whether the optimizer smiles at you or not, and it's generally a hack. And in C++ 11, now there is a better way. All we have to do is write explicit operator bool. So if you write explicit operator bool, this is an explicit conversion function. And what the compiler says is, OK, I will consider smart putter conversions to bool only in contexts that really obviously want a bool. Bool is actually kind of special cased. So in addition to something, let me comment this out for a second. If I say bool b parenthesis p, this is explicit. This is what's known as direct initialization in C++ 98, 03, and 11. Because you wrote this parenthesis here, C++ says, oh, wow, you're really trying to construct a bool from smart putter. OK, I will go ahead and invoke an explicit conversion operator. And then if you're testing something in a Boolean context, like if, or the operand of not, or something followed by logical and or logical or, there, even though you're not constructing a bool with direct initialization syntax, C++11 has been enhanced to say, oh wow, you really do want a bool. Okay, I will consider invoking an explicit operator bool. So in this case, this will compile. Let me save this, and there we go. And I've got a warning here that B is uninitialized. Here I can just silence that by casting it to void. There we go. OK, it compiles, and it's still Boolean testable, and I can directly construct a bool from P. However, attempts to just convert P to a bool in a non-explicit context will fail. This is something that we could not prevent from compiling in C++03 without resorting to horrible hacks like conversion to pointer member. So if I say bool B, let me say bool B2 equals P, this is what's known as copy initialization syntax. This is not willing to invoke an explicit conversion. So this will fail to compile, which is desired. Let me save and compile. And here we go. Error. Initializing. Cannot convert from smart putter to bool. No UDC available that can perform this conversion, or the operator cannot be called. And the reason why it can't be called is I marked it as explicit, and this is an implicit context. This is exactly the same rule, this whole equal, not considering explicit stuff. If I said something like vector int, vector has an explicit constructor from size. So I could say v, and I want, here, let me make this a little less confusing, something like vector string. I could say, OK, I just want 10 default constructed strings. This is considered explicit enough to invoke v's constructor from a size. However, if I tried to say v equals 10, this is no longer considered explicit. This code looks weird to C++ programmers, and it looks weird because the compiler won't compile it. You can't implicitly convert an integer to a vector. That would be weird. If you have a function taking a vector of string by value, by const reference, whatever, you can't just like pass a 10. That'd be bogus. Vector's constructor from size is locked down by being marked explicit. That was a constructor. Now we can do the same locking down on conversion functions. So let me erase this. If I've got a function here, imagine I've got void func taking some bool. I don't even need to give it a name, and it's going to do stuff. Then if I were trying to call this function with my smart putter, this is trying to implicitly convert smart putter to bool. I haven't directly said that I want to treat it as a bool. I definitely haven't initialized any named Boolean out of it. I'm not trying to test it in an obviously Boolean context here. I've just got a function that says it wants a bool, and I'm trying to pass P to func. By being explicit, this will fail to compile. This is good. I don't want this horrible code to compile. Bam. Void func bool, cannot invoke, cannot convert parameter 1 from smart putter to bool. Again, no UDC. Can be called. So this is great. And then finally, if I've marked this as explicit, the original motivating example, trying to multiply some smart putter by some integer, this will also fail to compile, because multiplying is not a Boolean context. I'm not trying to test P here. I'm just trying to treat it as an integer. And because I've marked this as explicit, it will not be invoked, which is great. So here I will save and execute, and here we go. Now we get a wonderful compiler error. I've never been so happy to see compiler errors. Here we get binary star, no operator found, which takes an LHS of type smart putter, or there's no acceptable conversion. And then it talks about what it could have found. It would be willing to multiply a bool times an integer, but it just can't get from smart putter to bool because I've marked that conversion operator explicit. So this is basically wonderful. You can also use explicit conversion operators with types other than bool. You could say explicit operator stood string, explicit operator whatever, and again, it would only be considered in contexts that are considered explicit enough to really demand the thing. But by far, its primary use case is explicit operator bool, where you just write this very simple thing, and you no longer have to worry about bizarre stuff like multiplications and divisions and modulo compiling. So that's great. Let's see. Now, next, default template arguments for function templates. Let's see what that looks like. I actually have a pre-baked example here. So we have seen how to write template functions and class templates, but then there's one curious asymmetry, which we saw in part 5, that if we've got a class template, we can explicitly specialize and partially specialize it. If we've got a function template, we can only explicitly specialize it. We can't partially specialize it. Well, that restriction is still there in C++11 because it's not really a big deal. As I mentioned, overload resolution handles most of the times you'd want partial specialization. But there was another asymmetry in C++03. And that was the fact that if I'm writing a class template, I could say template type name t equals some default, like int or vector, whatever, class blah. And this is totally valid C++03. But if I've got a function template saying template, type name t, func taking, I would need a return value, func taking, some t here, whatever. C++03 forbade me from adding default template arguments to function templates. So this here, this equal hint here, would be bogus in C++9803. That's kind of weird. And this asymmetry was actually a relic of C++98 standardization. Either limited compilers or just the state of the specification at the time meant that they couldn't really put default template arguments here. And in C++11, they realized that this restriction was not necessary at all, and it was actually preventing useful code from compiling. So in C++11, this restriction has been lifted. Now you can say t equals int on both class templates and function templates. And this is actually quite useful. So let me dig up my example here. Oh, no, I've got it here. Here we go. A little more than I just want to type in on the fly. So let me delete this. OK. So here's a sort of realistic example. Whenever I present examples, I try to present something that's at least kind of realistic rather than completely contrived. Imagine, after including all of my various headers, that I'm trying to write a container-based sort function because I would like increased convenience, and I don't want to have to pass begin and end iterators to my STL algorithm lowercase sort all the time. So in C++03, I could write this with two overloads. Let me just show you what that would look like. I would write, copy paste, I should have had this to begin with, 1, 2. I would have a plain overload that just took a container, like this, and then I would have a second overload that took a comparator, like this. And then here I wouldn't need this at all. Okay, so this would be C++03, where I would say, OK, I'm writing a container-based sort, and I'm taking some container by modifiable reference, and I just want to call stdsort with cbegin and cend. And then sort also has this customizable version where I can tell it how to do the sort, perhaps reversing it or comparing strings by their lengths, whatever. I would need to provide a second overload, taking an arbitrary functor and then passing that to sort. And I could not unify these in C++9803. That's kind of sad. In C++11, I can, with a single wrapper, and the way that it looks like is this. So I say, OK, I'm a template, and I take some arbitrary container. I need to know what container you're giving me, so that cannot have a default. And then I'm also taking a functor to compare things. However, if you don't give me one, I will default the type to be stdless, which is what stdsort would have used anyway. And I need to tell it what type is going to be compared. But since I see the container type, I can reach into it and grab its value type. This is just the element type. And then here's my sort function. I always need to take the container. Then I take the functor, and I also have a default function argument where if you don't pass a second function argument here, I will just attempt to default construct whatever type I have. And if you didn't give me a type, then I'm going to use stdless. So I have both a default template argument and a default function argument. And then I always pass the functor to sort. And if I didn't get one from the user, then I'll just be passing stdless of value type, which is what the two-argument version of sort would have done in the first place. So then I can have a print function, and I can have an array, and I can construct a vector. Here I'm not using initializer lists because we haven't implemented them yet in the standard library. I can print out the vector, sort it, print it out, and then sort it, and then explicitly pass a comparator to reverse it. I'm just proving that I can call sort either with a functor or without. So I save this, and if I compile and run, here we go. This was originally written from a very wide window on my dev box. The original list of primes is just completely unsorted. If I then call my sort wrapper without a second function argument, then it says, okay, template argument deduction, I figure out what C is, it's a vector. Oh, but you didn't give me anything that I can deduce F for. Okay, I'm going to use std_less of, and then the value type is int. And then it's got the function argument here, and then because we didn't pass a functor as a function argument, it's like, oh, I'll just default construct a std_less. So then I get my primes sorted in increasing order because I used std_less by default. If I explicitly pass std_greater of int, then all of this default template argument and default function argument stuff is ignored, and I actually use the greater int functor that was passed in, and I reverse my sorting. So this is nice. I get 2 wrappers for the price of 1, simply writing this here. By the way, in the Portland, Oregon C++ Standardization Committee meeting that I just got back from, I had a proposal to simplify the syntax of operator functors. It was actually voted into the standard, and it's on track for C++ 14. With that, which we will be implementing in VC shortly, but not in the CDP, you would actually not have to say any of this. You could just say less empty diamond, which is actually even more convenient. But that's just an unrelated aside. I wanted to point it out, how cool it is. Okay, so that is default template arguments on function templates. It's simply lifting a restriction and allowing you to write code that probably when you were learning templates for the first time, you probably tried to write it. And then you were confused and you said, wait, why doesn't C++ 03 permit this? And there was actually no good reason for it denying it. And now C++ 11 has lifted that. So that's cool. Let's see, what's next? Ooh, delegating constructors. Okay, I need to write an example for this from scratch. This is actually a very nice feature. It allows you to write constructors that will call each other, which can centralize your code. So imagine that I have a class here. I will say, I'll just say struct, because I'm lazy. Struct meow. And meow is going to have maybe a bunch of data members. Let's actually have a string here. Okay. Okay, I'll make it a class. I feel bad if I have public data members with something that has constructors and other member functions. Private, okay. So imagine I've got some data members here. I've got an int n, an int x, some double d. I don't like floating point very much, but I'll put that in there. And then some string s. I'm very, very inventive with my member names. Okay, now imagine that I've got something like a default constructor, some meow, doesn't take anything, and I need to go initialize all of these things. So say I want, mn to, 1729, and then mx, initialize that to 1, 2, 3, 4, some double d, and then some string s. Like this. Okay, default constructor, that's nice. And if this is the only constructor I have, well, that's not so bad. But imagine I have more constructors. Imagine I'm writing something like, okay, I've got some meow, and here I'll take an int, n, and I will actually store that in both my integers, something like mn, n, mxn, md, and then here I'm just going to, again, use 3.14, and then ms, here I could say meow. Like this. Or imagine I've got yet another constructor. Here I'm like, okay, meow, and I'm going to take a whole bunch of things. Int n, int x. Oh, and this constructor, because it's from a single integer, should be explicit. Int x, and then double d, and then const string ref s. And here I'm just going to do a member-wise init, mmn, mxx, mdd. Okay, so this is getting kind of repetitive, but imagine I really want to provide all of these constructors for convenience. Okay, in C++ 98, I could do something like write a centralized init function that would take arguments and then go assign stuff to each of these data members. However, that's not really perfect because data members have to be constructed in the constructor before they're ever assigned to. You can default construct them, but that may be potentially expensive. You may have to go zero out stuff or potentially allocate memory for some classes, whereas directly constructing things would be more efficient. And yet in C++ 9803, you can't have constructors calling each other. In C++ 11, you can. This is called delegating constructors, where one constructor delegates to another. So imagine here, I could have this constructor taking the four things. Say I'm going to call this one, my does everything constructor, and I want to write these other ones in terms of it. So instead of all of this stuff, I could just say, oh, I would like to construct my meow with the numbers 17, 29, 1, 2, 3, 4, 3.14, and then meow. Okay, that's cool. And then I will still have a body like this. And here, my explicit constructor, taking n, I want to replicate the n's and then have 3.14 meow. So I can just say, oh, meow of whatever, comma space, comma space, comma space. And I can still put things in their constructor bodies. So I can say here, I can just print the signature, just to show you what's happening. This. And then here, I can also print the signature. Like this. Relying on my brain to create red squiggles when I type something wrong. And then for the default constructor, let's do this. There we go. Okay. So let's see what happens when I've got all this stuff, and then I construct various meows. Let's start with just a meow m1 with no arguments. Let's start with a meow m2 from some integer, 9, and then meow m3 with all the things. I don't even care what they are. 0.0, and then some empty string. Okay. And to make the output clear, let's put in some dividers. Like that. And copy again. Like that. Okay. And hopefully this will compile. Yep, that looks good. Of course, it'll explode horribly because I mistyped something. Let's see if I'm lucky. Hey, cool. I am lucky. Okay, so what's going on here? Here I wrote something that was illegal. In C++ 9803, I wrote a constructor trying to call some other constructor. In C++ 11, this is okay. You essentially have an outer constructor delegate to some inner constructor. So I'm saying, okay, this meow here, this is a real constructor that goes and initializes all of its members and does stuff. If I default construct a meow, I would simply like to go invoke this other constructor with these arguments. I can put anything I like here. And then this constructor's body will run. So I'm going to see, because I first constructed meow m1 with no arguments, this constructor will run first. It'll say, okay, meow int n int x double d const string ref s. So I called this, it initializes the data members, then it ran the constructor's body, and then this constructor returned. But I can still do more things in my default constructor. So after this inner constructor returns, then I can print out things or initialize members further or whatever, just like I can in ordinary constructor bodies, and this gets printed out afterwards. So that's nice. Here I've got this meow int n doing the same thing. I'm going to call this inner constructor, and then I return to the outer constructor's body, and I can print out meow int n. And then if I directly call this constructor, it does its usual thing. I can also go more than one level. So here I could say, oh, this default constructor, I would like to call this int constructor. So I'm just going to say meow of 17, times 29, whatever. So I'm going to have the default constructor call the int constructor, and then that one calls this other one. This is totally cool. So if I save this and compile and run, can I convert to meow x? From int to const meow ref, constructor for class meow is declared explicit. My brain is telling me that this is a compiler bug that I need to report, because this is explicit. Okay, I'm going to have to report that to Jonathan. Let me get rid of the explicit here just to make it compile. Or I guess I could add a second int. Yeah, I'll just have one there. Okay. Yeah, because if I say meow parenthesis, that is considered explicit. I should be able to invoke explicit constructors there, even without looking at the standard. Okay, so this works. This showed what I was trying to show initially. If I have my default constructor, I can have that invoke a single arg constructor that then goes and invokes a 4-arg constructor and initializes the members, and then the bodies execute in reverse order. The innermost one prints out something, then it returns, the int1 prints out something, and then it returns, and then the default one prints out something, and it's done. So this is a very useful way to centralize your constructors rather than having init methods that aren't really ideal or writing out very spammy function bodies. There's also something interesting relating to exception handling, and this was actually new to me. I learned this at BoostCon C++ Now 2012. If you have an outer constructor that delegates to an inner constructor, okay, like this one here, and imagine that this inner constructor successfully executes, and then it returns, and then something in this outer constructor's body throws an exception. In C++ 98, the rule is that if a constructor exits via an exception, that object was never fully constructed. So its destructor will not be invoked. All of its fully constructed bases and members will still be destroyed, but the object itself will not have its destructor run. This is just a classic C++ thing that you need to be aware of. In C++ 11, this is still true with a twist. As soon as that inner constructor completes, the object is considered to be fully constructed. That's nice. So if the outer constructor's body throws an exception, as far as the standard is concerned, this is just an ordinary function body doing things. So if this exits via an exception, because that inner constructor successfully completed, the destructor for the whole object will be invoked. This was actually new to me when I first learned it, but it makes sense. And this can actually be a very nice way to avoid having to write try-catch blocks and other things if you're writing manual resource managers. At some point in the future, I would love to take advantage of this in classes like stdvector that do things like allocate memory, and then they need to make sure that none of their constructors can leak. In general, you should not be writing direct resource managers yourself very often, but if you do and you care about things like not leaking memory, then knowing the fact that delegating constructors interact with exception handling like that can be very useful. So that's delegating constructors. By the way, there is a related-ish feature called inheriting constructors in C++ 11. That's where you have a base class and you can say, oh, I, in my derived class, would like all of the base class's constructors, all of those signatures. That is a different feature, and that is not yet implemented in the CTP. They, just like raw string literals and Unicode string literals are similar-ish, but the CTP only contains one of them. Okay, so let's look at uniform initialization before we get to the star of the show, Variadic templates. So here my example will be very short. If I had initializer lists, I could show you other cool things. But with uniform initialization, this is some neat syntax that sort of simplifies what grew to be rather complicated ways to initialize stuff in C++ 9803. In C++ 9803, and you can read the papers for the rationale here. I'm not a core language expert, so I can't tell you in detail all of the problems that this solves. But you've got multiple ways to construct things. You can say things like, okay, let's construct a string s from meow with copy initialization syntax, or you can construct a string t from per with direct initialization syntax. Okay, that's kind of interesting that one will invoke implicit constructors and the other one will not. And if you're trying to default construct something, this is just a classic gotcha that always gets newbies. If I'm trying to say, like, string x, if I want it default constructed, I need to just say semicolon. If I try to say string, x2 paren, uh-oh, this is a horrible bug. In C++, even into 11, what this is saying is I'm declaring a function, x2, even if this is in local scope. And this takes nothing, it takes, no arguments, and it returns a string. I don't default construct anything. And this is very unintuitive to newbies. And as, experienced programmers, we just learn to never say parens here. But that's kind of weird. It's not uniform. And for integers, it's also kind of bad. If I say something like, int x, this is garbage initialized. This is just full of, whatever random bits the compiler had. I can't really look at it. But if I try to say int x paren, then that would, declare a function. I could say something like int y equals int paren, and this is actually guaranteed in C++ 03 to give me a value initialized int, which is 0. But this is horrible. It's not uniform. There's all these special cases. Ugh. And also, just to twist the knife, if I've got something like a double D, actually no, if I've got something like an int z, I can also get truncation when I initialize. So if I'm initializing from some double, like 12.34, this double will be truncated when I initialize the int. That's data loss. That is actually kind of yucky. And again, C++ 9803, it really wants to compile your code. So if it sees truncation, it's like, cool, I'm just going to do it. The compiler may or may not warn, but the fact that it must compile is kind of obnoxious. Uniform initialization searched the keyboard frantically for any other characters it could use. Parentheses were taken, angle brackets, templates are kind of using, but it used braces. So if you use braces, this is the new C++ 11 uniform initialization syntax, where I can say something like int x brace 1729, and this initializes the int from 1729 as usual. I can also do this with classes to pass arguments. There's a whole bunch of special rules, but this is the most basic usage. So here, if I save this and compile, I print out 1729, which is nice. One thing though, because they were inventing new syntax for initialization, they were also able to go back and close this loophole about narrowing, truncating conversions. So here, I've got this code here protected by boom. If I have something that would truncate, for example, a double to an integer, uniform initialization is not willing to do that. I will get a compiler error, which is desirable. And this is a difference, an intentional difference between uniform initialization and the old style initialization with either equals or parentheses. So if I attempt to compile this and I define my little boom macro, deboom, I get a compiler error. It says error, initializing, cannot convert from initializer list, which is these braces here, to int, and it says this list initialization requires a narrowing conversion from double to int, and it is not willing to do that. This is a feature that I get this compiler error. Eventually, when we get initializer lists, you will also be able to say things like vector int v. This is the same feature but different, and with either direct braces like 11, 22, 33, or if you like me, like the old style syntax with braces, you could say 11, 22, 33, and this will construct a vector with what is known as a std initializer list. This is the type. And it will invoke a special constructor on the vector that will give it these contents, which is extremely convenient. You don't need to say pushback, 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 or you don't need to construct an array and then range construct a vector, which is kind of obnoxious. But that requires standard library support, and we have not yet gone and decorated all of the standard library containers with such constructors. We will in the very near future, but not in the CDP, so just so you're aware. Okay, so that is uniform initialization. Now for variadic templates. I would like to start with a simple, sort of realistic example. Then I want to do crazy things. But first, realistic example. So here we go. I've got my thing here. And yes, this is what I want. Okay. And I'm going to need to maximize that because that is kind of small. Okay, so one of the issues in C++ 11 is that we've got shared putter and make shared, which is awesome, as I've talked about in my Going Native 2012 presentation. We've got unique putter, which is a way better replacement for auto putter, which is now deprecated. But there is no make unique. So let me just use this as a scratch pad. If I've got a unique putter and I want to construct it, I would need to say unique putter p, and then I need a type, some t, p, and then I'd need to new up a t and give it args, args, args. This is obnoxious because I need to mention t twice. T is probably more than a single character, and I need to write new. This is actually getting in the way of us giving a very simple rule to users, which is never say new, never ever say delete. If you follow that rule, your program is actually structurally armored against memory leaks and resource errors and things like that. And we are almost there. You can use vector instead of new bracket bracket. You can use shared putter instead of scalar new and delete. But if you're using unique putter, you actually have to say new. You immediately give it to unique putter, so you don't say delete, so that's cool. But it adds the special case to the rule of never say new, never say delete, except in direct resource managers like trees or very high performance data structures that you probably shouldn't be writing all of the time. Only experts should be doing that. So that's obnoxious. And there's also a gotcha where if I've got a function, say I've got some function, whatever, and it's going to take a couple unique putters. Let's suppose that I'm writing them as being taken by our value reference because I want to move from them. Unique putter, and let's say int, ref, up1. Say I've got a couple. This is a classic gotcha with shared putter that is also true for a unique putter. up2 like this, and it goes and does whatever. And suppose I'm trying to call my func, and I'm going to say, okay, I want to call this, and I don't have unique putters lying around. I just want to construct some objects, here ints, and then just pass it to function. So I'm going to be lazy. I'm just going to construct them on the fly. I'm going to say unique putter int, and I'm going to write bad code. This is bad. Don't do this. New int, and then give it something. And then another unique putter. This is extremely bad. It hurts my fingers to type this. New int 34. Close, 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 semi. This is a leak. This is a memory leak, despite the fact that I'm trying to be careful by using unique putter. The reason why is somewhat arcane. C++ has an unspecified order of evaluation. And in something like this, what happens is that it is totally allowed for the compiler to construct this new int 12 and then just store a pointer to this newed up integer somewhere on the stack or some temporary location. Then it could go evaluate this new int 34 and then go store a pointer to that somewhere. And then go construct maybe this unique putter or this unique putter and then the other one, and then actually go invoke func. Now if all of that succeeds, we're fine. We constructed unique putters. They will delete their newed up ints when they are reset or assigned, blah, 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 and everybody's happy. But what if an exception was thrown? For example, by memory allocation. If I knew up this int, and then C++'s unspecified order of evaluation says that this is next evaluated, and this new int34 throws an exception, then this raw pointer here was never given to unique putter. It will leak. That is bad. If it's an int, it leaks a little bit of memory. If it's something like a file, a socket, a lock, a texture, an hwind, it's going to leak some resource. That would be really bad because the operating system wants me to, give it back at some point. So the way to guard against this is write make unique like I'm going to do below. Or if you don't have make unique, the rule is always, if you're going to new up something, give it to a named unique putter or shared putter. Because if I say unique putter p, and I give it a name, here's a name, and then I say new int blah, or string args, whatever, this new will happen. It'll either throw or not, and then I will construct the unique putter. And if I wasn't able to allocate the int, then I'm fine. I didn't leak any memory. And if I did, then I hand it off to the unique putter, and now its destructor is guaranteed to release memory if then I throw an exception later, for example, by constructing a second one. This is safe. So if you just follow the rule, okay, always immediately give nude things to either named unique putters or named shared putters if you don't want to use make shared, then you're safe. But it should be nice to have a maker. So you can write one without Variadic templates, but you need to go spam out a bunch of overloads for n number of arguments. You need to pick a big N, like 5. Who would ever want more than 5 arguments? And that's obnoxious. With Variadic templates, we can now do better. So here, I'm including all the headers I need, and here's the syntax I would like. Then I'll show you how this is implemented. So I'm going to say, okay, I am writing a function make unique. I need to be told what type of unique putter to return. I want to return a unique putter t. So I will demand that this be given as an explicit template argument. This is okay because the function is designed to take t as an explicit template argument. So I'm going to start off by saying template type name t, comma. And then because t does not appear in the signature of my function, it cannot be deduced. It must be explicitly specified. So my usage looks like make a unique int and then give it some arguments. So the arguments, the way this works is I want to accept an arbitrary number of arbitrary arguments. Variadic templates will handle the arbitrary number part. Perfect forwarding will handle the arbitrary arguments part. So what I do is I say, okay, I want type name ... args. And this ellipsis here, you can think of type name ... as being a special unit. Notice my spacing here. Other people put spaces in other places. They are monsters. Please don't follow them. Follow my style. If I say type name ... args, args is what's known as a parameter pack. And it will expand as necessary to accept an arbitrary number of stuff. And then here I want to take perfect forwarding. So I say, okay, make unique takes args ref ... args. And you can think of this as saying arg0 ref arg0. You can hear me pronouncing the capital letters there. arg1 ref arg1, comma, blah, blah, blah. And then within the body here, I'm going to go call some helper function. And eventually what I'm going to do is I'm going to say return unique putter of t, new up a t, and then go forward my arguments. What I would really like to say is forward capital arg0, parenthesis little arg0, comma, forward capital arg1. I guess I can type this out rather than speaking C++. What I would like to do is say forward capital arg0, if I were writing like named arguments, comma, and this is of course stood for it, I've got it using a declaration above there, arg1, blah, blah, blah. Maybe arg2, you get the picture. I would like to sort of repeat this pattern for every argument that I've got, but I need to repeat it for each template argument and function argument. And the way that Variadic templates is specified is really, really cool. I can write an expression here, forward args, and I'm mentioning both a template parameter pack, this is capital args, and a function parameter pack, this is lowercase args. And then if I put ... outside that whole expression, it will be stamped out repeatedly for however many things I'm actually being passed. This is really unbelievably cool. You can do all sorts of things. If you have multiple packs, you can zip them together. You can expand one but not the other. All sorts of neat things. But this here is the very simple pattern for how to write an perfect forwarder that accepts an arbitrary number of arbitrary arguments. All I got to do is say type name ... args, and then take args ref args, and then inside my guts I say forward args ... If I just say this, then you don't need to know about all the horrible things that perfect forwarding and Variadic templates are doing. It is just perfectly transparent. It accepts arbitrary stuff and passes it along. So in here, I'm just using an int. I could also construct a string if I wanted to prove that this will work. But one argument is fine. Okay, I guess I can show you a string. Include string. I can say auto s is make unique string. String is a bazillion constructors, but one of them is I want to construct a string from n number of characters, so I want like 5 x's. Okay, 2 arguments, that's cool, and they're of different types, int and char. And then I just want to print that out. Deref x and l, because it's unique putter. Okay, and then I'll show you what the guts of my helpers are doing, but first I just want to show you the usage. So let's save this, hope I haven't mangled anything horribly, and see what the compiler gives me. Oh, I don't want to define boom, that's for sure. And x undeclared identifier, because I said s and x, this should be s. Awesome. Okay. Awesome. So I can say make unique int and give it a single argument, and it'll go new up an int from that argument, and then I can go print it out. Or I can pass 2 arguments, a 5 and a character x, to strings constructor, and this arbitrary number of arbitrary arguments will be forwarded on through make unique to its helper to this new, and then strings constructor will see it being given this int5 and the character x without interference from all of the layers of stuff in between. This is exactly what makeshare does makeshare does a little more complicated, but it's the same idea. And then I print out the 5 x's because that's what my string contains. Now here I'm trying to be fancy. I would also be able to to do this, and this is something the shared putter does not have. There is a unique putter that can own an array, and the syntax for that looks like unique putter This is known as unique putter to arrays with runtime lengths. If I say something like unique putter int bracket bracket, say R, or I'll just say P, then here I would be constructed from something like a new int of 5. And then this gains an operator bracket bracket, so I could say something like P of 0 is 1, 2, 3, and so forth. This is less powerful than a vector. In fact, I don't like this. I like to use std vector, but if you want something like this, which has extremely low overheads, then it's there for your use. And I would be able to like to treat this with make unique as well. And in fact, I could do something really cool. So I need a little bit of template metaprogramming, which is a fancy word that just means manipulating types at compile time. My make unique here, if I wanted to be simple and just handle unique putter to scalars, individual objects, then this body would have been all that I needed. But instead, I've got a helper here. And this is make unique helper, and I've got to pass a t, this explicit template argument. I would like to do something different, based on whether the user asks me to construct a unique putter to either a scalar or an array. So here I'm going to use type trace to ask, hey, is this thing an array? This will be false for something like an int or a string, but it'll be true for an array without dimensions, like int bracket bracket. And this thing will either derive from true type or false type. If this is false type, then it's not an array. I just want plain old unique putter scalar, and that's what I've got here. But if it is an array, I would like to go construct an array, give that to my unique putter, and initialize it. And I can do this all with Variadic templates. I would like, though, to have a static assert. I do not want this thing to be misused. In particular, I do not want somebody saying I do not want somebody saying make unique int 5 like this, or without a space, whatever, and then give it some args. Even if they give me exactly 5 arguments, this does not parallel. Sorry, these dots may be confusing. I should say stuff. Even if they give me exactly 5 arguments, the syntax for unique putter array always has no bound. It always looks like this. I would like make unique to require the same syntax. So I can actually, using type traits, forbid people from passing bounds here. And for some reason, make unique putter itself does not forbid this with a static assert. It should. I will have to talk to the standardization committee about that. But the way I can forbid this is there's a type trait called extent. And if I know the t is an array, here t would be the array, either int with no bounds or int with some bounds. If I ask for its extent, this is just its dimension. If it has no dimension, with empty square brackets, then it's 0. But if the user gave me a dimension, then it will be non-zero. I want to static assert that the array's extent is 0. And if this is violated, I want to print out a nice error message saying, hey, make unique t of n is forbidden. Please use make unique of t empty square brackets. This is nice, and the static assert compiles away if it's true, so it has no cost. Then I would like to construct an array and initialize it with stuff. So I'm going to gloss over what I'm doing here. What I want to do is I want to say return unique putter of this array type. I know that t is really some array that looks like x bracket bracket, so I'm just going to say t. That's fine. And then I need to say, OK, I want to new up an object, the element of that array. And this typedef u here is the element type of the array. Extent gave me the dimension of the array. If I use the type trait remove extent, this gives me the element type of the array. This is very convenient. Then I need to actually say how big this thing is. I'll get to that. And then I can now use uniform initialization to actually initialize the members of an array as I new it up. This is cool. And here I'm going to use forward args, dot, 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 to just spam out all of the arguments that I've been given. So I need the syntax. This is going to be with the call make unique int array 11, 22, 33. What I want to write is new int 3 of them constructed with braces from 11, 22, 33. Like this. Okay. Curiously, and this actually surprised me when I was playing around with this code, I must put a bound here if I'm newing up stuff. The standard does not allow me to omit it. I can omit it if I'm just at local scope and I'm saying, OK, I have an int local array like this with no bounds, and I'm just going to give you some arguments like, oh, that was page down, 10, 20, 30. The compiler statically sees that my initializer has 3 elements, so it says, oh, you're just an array of 3 ints. That's cool. However, the standard ease for newing up stuff does not allow you to say new int empty brackets, even if you give it some arguments like this. The reason why is that the syntax for new requires the type to be complete. This is considered an incomplete type. But after talking about it, I actually believe this is an unnecessary restriction. It made sense in C++ 03, but not in C++ 11, where you can actually initialize the things directly. So in the future, this syntax may actually be permitted. But as it stands in C++ 11 and in our current compiler, you must specify a bound. So given a parameter pack, either a template parameter pack or a function parameter pack, how do I get the number of things in it? I could write a helper template that would count recursively the number of things in this pack. And this is actually not too hard. This is actually sort of Variadic Templates 101. I could show you how to do it. It's not that hard. However, for once, the core language smiles upon us, and it says, OK, even though you could write this thing with a helper library, I will be nice and I will provide a dedicated core language construct to get the number of things in a parameter pack through the core language. And the syntax for that is size of ... args. The ... goes on the size of, indicating that it is a new special thing, and this will turn out to be 0, 1, 2, 3, however many arguments were actually given. Here I'm specifying the template parameter, although I could also specify the function parameter pack because both of them have the same dimensions. Note that if I said something different, if I said size of args, and this is just a gotcha that you may run into, if I said something like this, this will not do what I want. Sometimes I may want this, but not in this case. This will expand just like forward args args does. This would expand to size of arg0, comma, size of arg1, comma, whatever. Size of, you get the picture. So if my arguments were like int and int, then I would get 4, 4, 4. Because integers are size 4 on our platform. Or if they were int and char, I would get 4 and 1. And that is maybe desirable in some cases, but not if I'm trying to count the arguments. So the ... gets attached to the size of, and not afterwards if you want to just count the arguments. And this, as I have shown, all compiles and works and allows me to construct either a unique putter to a scalar or a unique putter to array and give it initializers. The reason why I prototype this is I'm actually planning to propose this to the library working group at some point in the near future, possibly for the next meeting in April. I wasn't able to nail it down for the most recent meeting. So you may see this in a standard library soon. But until then, this is how you'd write this sort of thing by hand and any other Variadic perfect forwarders that you might like to do. So that's basically it. I don't have time to get to my crazy examples. Maybe I'll show them in the comments. I have a couple examples that show you how to sort an array at compile time, which is fun. You can do that with Variadic templates. And I've also got this funny thing where I can compute sequences of the Collatz conjecture using Variadic templates and computing things like 3n plus 1 by spamming in arguments, args ... args ... args ... It's completely silly. But I just wanted to see if I could do it, and it taught me some things and found some compiler bugs as I was going along. But at least I had time to show you this realistic example. So that does it for the features in the Microsoft Visual C++ Compiler November 2012 CTP, or as we internally codename it, Milan. In the future, I will be covering other features as we add them to further releases of this project. And of course, going back to C++ 03 and C++ 11 features in the rest of Core C++. So let me know what you'd like to see in the comments. See you next time.